All right, so let's get started. Today I want to cover 5 examples and wrap up chapter 5. The first 4 examples are rather straightforward. Actually, all of the examples are straightforward. The only difference is that the math that we do is with complex numbers. Other than that, there's no new analysis technique as such. So let's look at example 1. Example 1 and 2, for that matter, we are simply given an expression Vs of t is equal to the sum of two quantities. Okay, it does not matter that it's Vs of t, it's a voltage, it could be current, Is of t, does not really matter. What we are simply trying to show is that is the sum of two sinusoidal waveforms. Okay, so the first 2 examples, we deal with phasors, meaning the sinusoidal input voltage or current. The second 2 examples are relating to inductor and capacitor. So when you are asked to add 2 sinusoidal waveforms, the first thing you should look at is the frequency. In this case, omega. The value of omega is not given to us, but it does not really matter because a phasor is a vector representation in the frequency domain. It does not contain any information about omega. So we do not need to know the value of omega to actually add these waveforms. But the important point to consider or to remember is that to add or subtract, the frequencies must be the same. If they are not the same, you cannot perform any operation on those waveforms. Okay, in order to add and subtract sinusoids or sinusoidal waveforms, the frequency must be the same. Must be the same. So it doesn't matter that the value is not given, but what is given to us is that both have the same value of omega. Make sense? Right? That's the absolute first thing you need to know. And that's it. From that point on, it's rather straightforward. So I would write out my expression Vs of t is the sum of 10 cos omega t and 10 sine omega t. So now I'm going to do a vector representation, and I'm going to do a phasor transform, write out the phasor quantity directly from the peak values, the magnitude, and the phase angle of the waveform. But if you remember, what I said was, in order to write the phasor transform, we have to convert the waveform into cosine. So we use the trigonometric identity sine x is equal to cos of x minus 90. We subtract 90 degrees from the waveform. So the first quantity remains the same. The second quantity becomes 10 cos of omega t minus 90. And that's it. That's all we need to do. Nothing else. So the phasor for Vs becomes 10 with a phase angle of 0 plus 10 with a phase angle of minus 90. That's it. As easy as that. You simply take the magnitude or the peak value from the time domain expression and the phase angle from the time domain expression and write down the phasor directly. And you have the polar coordinates for that vector. Now at this point, I would assume that most of you have a programmable calculator. You go ahead and program this in your calculator and it will give you an answer. And that's the answer. That's the answer to the waveform. For me, because I am set in my ways, I do not want to upgrade to a newer calculator. I keep using my old one. And so I would convert this into rectangular coordinates and perform manual math. 0 minus J10, and therefore the phasor for Vs is now 10 minus J10. So I'm going from polar to rectangular conversion here, and then perform the math, which is the addition, and then I get 14.14 with a phase angle of minus 45. Is that the value that you obtained, or whoever did the calculation? Did you all obtain the same answer? You obtain 14.14 with a phase angle of minus 45. Yes or no? Or you haven't cracked open the worksheet yet? Yes. Question? So in this step, I simply did the phasor transform, right? So 10 angle 0 plus 10 angle minus 90. Then, as I stated, if you have a calculator, you can directly program this equation into your calculator and should directly give you this answer. So it's a direct calculation. If you don't have a programmable calculator, then I would perform, since I need to perform an addition, I transformed the polar coordinates into rectangular coordinates. So 10 with the angle of 0 becomes 10 plus J0 in polar coordinates, right? 10 with the angle 0 is a vector lying on the x-axis, flat. So the real portion is 10, imaginary portion is 0. Make sense? And then it's 10 with the angle of minus 90. So length of 10, angle of minus 90 points straight down on the imaginary axis. So the rectangular coordinates for this, real portion is 0, right? It's on the axis, plus a length of minus 10 on the imaginary axis. So 0 minus J10. So there are equations, all of these quantities, the polar coordinates and the rectangular coordinates together, simply the sides of a right angle triangle. So there are equations. You can derive either one of these manually by using trigonometric identities. So I don't have time in class to actually go through those equations, but what I'll do is I'll write it up on a worksheet and I'll post it on the website, or I will add it as a slide onto these OneNote notebooks. Okay. But if you did this calculation, did you obtain this answer? Did anyone perform this calculation? Chapter 5. Again, if you have not yet practiced, I urge you to practice with your calculators. There are tons of websites out there that will have a tutorial on using these, on using your own calculator devices to perform these functions. There are YouTube videos out there that will show you this, okay? Your fellow student peers would also know this, so just reach out to somebody. Yes. I would say complex number math or complex math with the model number of your calculator. And it should come up something. As practicing engineers in real life, if you have access, you would have access to websites or the internet. You could simply go online, and there are websites that have online calculators. You simply enter the numbers and it would give you the answer. But again, as engineering students, it would behoove you, each and every one of you, to actually learn how to do this, right? Or at least the basics. This is not just electrical engineering, as I mentioned before. This is just maths, right? So it's something you would use in your own fields also. So again, analysis technique as electrical engineering, The only thing we are talking about is the frequency must be the same, and then the phasor transform. After that is just math that applies to any field. Yes. You can't add or subtract, no. One final thing here is that the answer asked is as a function of time, the time domain, Vs of t. And so we have to perform an inverse phasor transform at the end, which, I mean, the words sound scary, but it's not. You simply take the magnitude of the vector, 14.14, that gives you the peak value of that waveform, Vm, and the inverse phasor transform is in cosine, so it's cos of the frequency does not change, it is not affected, so it stays the same, in this case, omega t, with a phase angle of minus 45. And that's it. That's your final answer. It's your final Vs of t. Yes. So 14.1, it's 14.14. That's the value of this waveform. It's a simple explanation on the real and imaginary axis. 10, meaning the real component is 10. The imaginary component is minus 10, right? And so if you try to find the phasor for this, you find the intersect, which is right here. And so 10 and minus 10, take either one of the triangles. It doesn't really matter which one you take, but you apply trigonometric identities and you get the length of the vector as 14.14. And then the phase angle here is minus 45. Anyway, these are all calculations that we used to do manually, but technology helps us save time, right? You simply enter the value of the coordinates and it just gives you a final answer. All right, so same thing for example 2. We have two waveforms, two quantities. We are simply asked to find the sum of those quantities, Vs of t. So again, here, V1 of t is 20. Actually, you know what? I'm going to write up the phasor directly. So Vs, phasor for Vs is 20 with the angle of minus 45. So 20 with the angle of minus 45 from here. And then this expression becomes 10 cos of omega t plus 60 minus 90. And so this becomes minus 30. So V1 of t is 20 with an angle of minus 45. Second one is magnitude 10 with a phase angle of minus 30. Again, second, V2 of t is in sine. So sine x is equal to cos of x minus 90, meaning cos omega t plus 60 minus 90. I subtract 90 degrees from the phase angle. That gives me a phase angle of minus 30. So you have two vectors. The sum of these two vectors, well, again, you can perform a conversion or program it into a calculator. It should give you a value of 29.77 and a phase angle of minus 40. So you perform this at your own, in your own devices and verify or compare your answer to what I obtained. This conversion gives me 14.14 plus 8.66 minus J5. So I'm performing a polar to rectangular conversion because I need to perform addition on these quantities. Adding up the real parts together gives me 22.8. Adding up the imaginary parts together gives me minus 19.2. 1,4. Since I need to perform an inverse phasor transform, I'm going to perform a conversion from rectangular to polar coordinates. That gives me a vector with a magnitude of 29.77 and a phase angle of minus 40.0125 degrees. And so final answer for Vs of t is a peak value or magnitude of 29.77 cos of omega t minus 40.01 degrees. All right, questions. Again, anyone perform this calculation? Same answer? That's all it is. Polar and rectangular coordinates are just the sides of a right angle triangle. Okay, you can find them manually by using trigonometric identities. Okay, and again, you can find this information online easily, but I will write it out or type it out in a slide and I will attach it to the notebook. Okay. It's not something that I would expect you to sit in an exam to do. It just takes longer, right? So I don't want students to waste their time on something that is easily done using a electronic tool. Okay, any questions? This is simply two phasors. We're simply adding them up. We're summing them up. That's all we're doing. Nothing else. There's no circuit analysis here. It's simply the math. So I just want students to get comfortable with this before we move on to different examples. Yes. Yes. Yep. Yep. That's all we're doing. So as I like to joke, I'm getting too old. I love technology, but for some reason, I don't want to upgrade my calculator. I love using new technology all the time, but I don't know. It's a block with me. So again, it's a programmable calculator like what students use nowadays. You can simply program any equation in any form, and you should be able to obtain an answer directly. I will state this, though. If you do program it directly, then you better be an expert at using your own calculators, right? Because if you make one mistake, one error typing this, like if you instead of minus, you put in a plus, you might end up with the incorrect answer at the end. So if you go directly from, let's say, if you go directly from this step to this, a direct calculation, sorry, not there, from here. And if your answer is incorrect, I would not be able to give you partial. I mean, I give partial credit for most of the work that is shown. But if all you have is, the first equation and the final answer and nothing in between, I can give you a lot of partial credit. So if you have multiple steps in between, then I can give, credit for that. Always tell students, even if you don't know anything, just write something. Because if the work is not shown, if it's blank, I cannot give any credit. At least if you write something, you show me an effort, I can award some points to it. Okay. So it's the same concept here. So you'd better be very confident in your abilities. So you need to practice, and practice. Again, so worksheet has been on the website since the beginning of the quarter. So if you have not yet opened it up, go ahead and open up that worksheet, practice, make sure you get the right answers, right, for complex number math. Okay, so examples 3 and, any questions, any final questions before I move on? Okay, so examples 3 and 4 simply deal with an inductor and capacitor. In both cases, we are given the voltage and the value of the inductor and the capacitor, and we are asked to find the current. Okay. Now, think back to chapter 3. If you wish to find the current for an inductor, what did we do? Voltage for an inductor is given as L di over dt Inductor current is the integral of the voltage, right? Inductor current is integral of the voltage. So normally we'd have to do that, but because we use phasor transforms and complex numbers, we can reduce this problem, this differentiation or integration, to a simple application of Ohm's law. Okay. So that's what we're going to do for example 3 and 4. We're simply going to apply Ohm's law, perform complex number math, and that's it. We'll have our answers. Okay. So let's look at example number 3 first. Example number 3, we are given an inductor of 0.25 Henry. And let's see. VL of t, voltage of the inductor as a function of time, is given to us 100 cos of 200t. So first thing, extract as much information as you can from the problem statement. Omega is 200 radians per second. Phase is 0 degrees. And the peak value, or Vm, which actually I should have written it first, is 100 volts. Vm is 100, phase angle is 0, omega is 200. Directly write down the phasor for VL. There's a peak value of 100 volts, phase angle of 0. Then find ZL, impedance of the inductor. And impedance for the inductor ZL, omega L, with an angle of 90 degrees. So it's 200 times 0.25 with a phase angle of 90 degrees. And therefore ZL is 50 with an angle of 90 degrees. And the unit is ohms. Okay, do not forget the units. Okay, easy enough. Again, these are equations you can have on your equation sheet, but you should know how to work with those quickly and efficiently, and correctly for that matter. Okay, omega L with an angle of 90 degrees. That would give you the answer in polar coordinates. In rectangular coordinates, it's simply j omega L. And so you could do ZL as j omega L. It'll give you the same thing, j into 200 into 0.25. And so it'll be j 50 ohms. I'm just showing you both. We don't need both. We don't need the rectangular coordinates because what we're going to do is V equals IZ. I is equal to V over Z. We're going to perform a division. If you're performing division, it's easier to do in polar coordinates, not rectangular. Yes. That's the formula. Omega L with the angle of 90 degrees. So remember, the current and the voltage for an inductor is out of phase by 90 degrees. So the voltage leads the current by plus 90. So if the current is at 0, voltage would be at plus 90 degrees, pointing straight up. It'll make a little bit more sense when we get to example 5. But again, no circuit analysis here, not yet. We haven't done any circuit analysis yet. Still, again, just math. We have a voltage given to us. We directly write down the vector representation, which is the phasor, and then applied, well, a little bit of circuit analysis here, but it's the straight standard equation, omega L with an angle of 90 degrees. And then phasor for the inductor current IL, let me write that we are going to apply Ohm's law. V equals IZ. So IL phasor is VL over ZL. VL is 100 divided by 50. So I'm dividing the magnitudes, and then the phase angles get subtracted. So 0 minus 90 degrees. So it becomes 2 with an angle of minus 90. In rectangular coordinates, it would simply be current would be, see, 2 minus 90, so pointing down. Final answer is as I of t. So you perform an inverse transform. So IL of t would simply become 2 cos of 200t minus 90 degrees. The unit would be amps. Make sense? Okay. Magnitude 2, phase angle minus 90. So it simply becomes 2 cos 200t minus 90 degrees. Yes. Current, amperes. So the units for everything remains the same. Impedance remains ohms. Voltage is volts. Current is amps. Oh, here, sorry. I just got that. It should be amps. One point I'd like to make is the impedance is not a phasor. It's a vector representation, but it's not a phasor. Okay? It's not a phasor. So it's not, you're not going to write out a time varying expression for the impedance. 1036. All right, any questions before I move on to example 4? Example 4 is exact same, except instead of an inductor, it's a capacitor, but it doesn't change our approach. So example 4, I'm given a capacitor. What I'm going to do is, again, extract information. So Vm is 100 volts. Omega is 200 radians per second. And phase angle theta is, again, 0 degrees. It's the exact same thing. There's no difference in the expression. So therefore, if I write out the phasor for Vc, it'll be 100 with an angle of 0, unit volts. Capacitor impedance Zc is 1 over omega c with an angle of minus 90. And so this is 200 times 100 microfarads and an angle of minus 90. Therefore, Zc is 50 with an angle of minus 90 and ohms. Apply Ohm's law, find current IC. IC is simply Vc over Zc. So that would give me, again, 100 divided by 50 and 0 minus of minus 90. That's 2 with an angle of plus 90 amps. Final answer in the form of time domain expression, IC of t is 2 cos of 200t plus 90 degrees amps. The two problems are exactly the same. It was just to show you how the impedance equation changes for both components, for the inductor as well as the capacitor, but the approach remains the same. Okay, we are given the value of the inductor or the capacitor. We're given the value of the component. We are given the voltage that is being applied, and we're asked to find the current. And so the approach remains the same. You find the impedance, apply Ohm's law, and you find the current. If you are given the current and asked to find the voltage, still remains the same. You would still find the impedance first. You would apply Ohm's law. You would simply take the current phasor, I, and then multiply it with the impedance and obtain your voltage. Make sense for everyone? Any questions before I move on to example 5? Mm-hmm. Oh yeah, that shouldn't be on there. Yeah, that shouldn't be on there. Or if at most I should have it as a phasor, right at the phasor for V of t. Okay, let's move on to example number 5. It'll probably take more than 20 minutes to get done. So if you need to leave at 11, feel free to do so. I will keep, I'll keep going until the solution is finished and, everything is being recorded. So everything should be on the lecture video. Okay. All right. So let's get started with example 5. We see a circuit which has 3 components, R, L, and C. All 3 components are on there. So the first thing I would tell students to do here is to draw out the equivalent impedance diagram. Okay, so the first thing when you see a circuit like this for AC analysis is to draw out the equivalent impedance diagram. And it's nothing except representing all the quantities with their complex impedances. Okay. R, of course, remains R. L is represented by its impedance ZL, capacitor with ZC. Vs of t becomes phasor for Vs. Doesn't this look familiar from chapter 2? Right? Again, analysis techniques do not change. They remain the same. So this is a problem from chapter 2, series parallel analysis. If this was a DC voltage you're applying to a 3 resistor circuit, what would your approach be? What would you do as a first step? Absolutely. So we'd find Req in this case. We'd find Zeq as seen by the source, meaning we'd remove the source. And we'd find Zeq between those terminals. So again, just because the source is AC and we deal with complex numbers, the analysis techniques do not change. Only the math changes, but the techniques still remain the same. So this, again, is, of course, R, ZL, ZC. Zeq in this case is simply R plus ZL plus ZC. We cannot add a resistor to an inductor to a capacitor, but we can add their impedances. Okay, we can add their impedances. So first step is to find ZL and ZC. We have, what do we have here? Vm is 100 volts. Omega is 500 radians per second. And phase difference theta is 30 degrees. The expression is given in cosine, cos of 500t. If it was not, you would convert it into cosine first before you write down the value of theta. Okay. If it was given in sine, then you convert, you subtract 90 degrees from the phase, and then write down the value of theta. Okay, so phasor for Vs would simply be 100 phase angle of 30 degrees, unit of volts. ZL is omega L, the angle of 90 degrees. That is 500 times 0.3 Henry. The angle of 90. So that gives me 150. The angle of 90. In rectangular coordinates, it is J omega L. So it would simply be J 150 ohms. It's just a habit with me that I find the values in both polar as well as rectangular coordinates. Just for me, it saves me some time when I go through the solutions. Okay, you don't have to do both of those. You can just do either one. Okay, we good so far? Okay, ZC then is 1 over omega C with an angle of minus 90. And omega is 500. C is, what is C? 40 microfarads, 40. And that gives me 50 with the angle of minus 90 ohms. I can also write ZC as 1 over J omega C. So it's minus J 50 ohms. Since I need to perform an addition, I'm summing up the three impedances together. I would use the rectangular form. So ZEQ is, again, it's R plus ZL plus ZC. So it's 100 plus J 150 plus minus J 150. The final value is 100 plus J 100 ohms. Also in polar coordinates, that comes out to be 141.4 with an angle of 45 degrees ohms. Okay, so all you have done so far is you have three resistors. You've summed up the three resistors in series to find Req. That's all we have done so far. Okay. Be good? Right. Now, if this was, think back to chapter 2. You have three resistors in series. You're applying a voltage. You wish to find the voltage across each one of those three components. What do? We can find the current. And what happens to voltage across a series connection of resistors? It drops, but it's divided. You could also apply voltage division. So if you don't wish to find the current, you can apply voltage division directly, which I will write up the equations here. I would encourage students to practice on your own calculators outside of class time. Okay, but let's first take it step by step. So since I found ZEQ first, we will find current I, then we'll apply Ohm's law again to find the voltage. So total current I is the phasor for Vs divided by ZEQ. Vs is 100, and this one is 141.4. The phase angles are subtracted. So it's 30 minus 45. This gives me an answer of 0.707 with a phase angle of minus 15. Time domain expression is I of t is equal to a peak value of 0.707 cos of 500t minus 15 degrees. Okay, simple application of Ohm's law, right? I equals voltage divided by the total impedance. And now you apply Ohm's law again to find voltage across each one of those, where V equals IZ. And so I can write VR, phasor for VR is I times R. Phasor for VL, inductor voltage, is simply I times ZL. And for VC is I times ZC. I'll give you the answers right now. VR, phasor for VR is 70.7 with a phase angle of minus 15. As a function of time, it would be 70.7 cos of 500t minus 15 degrees volts. VL is 106.08 . So VL of t is 106.08 cos of 500t plus 75. And VC, phasor for VC is, what is it? 35.35. 35.35 in amps. Oh, not amps, sorry, still voltage. (500t minus 105 degrees volts). Okay. Anyone performing these calculations? Do you obtain the same answers? And then VR of t. Okay. So again, if the final answer is asked as a function of time, is a V of t or I of t, then you have to perform the inverse phasor transform at the end. If it just says find the phasor, then you just leave it at that. Okay. So the equivalent equations for voltage division would be, let's see, it would be here from voltage division. Actually, what? Let's write it out on the side. VR would be a fraction of the source voltage Vs. The fraction is given by R over ZEQ. VL would be Vs times ZL over ZEQ. And VC would be Vs times ZC over ZEQ. The equations remain the same. The equations do not change. The only thing that is changing is the math. So again, You all need to be an expert at your own calculator devices. Again, it's not just for this class, it's going to help you as an engineer in general. All right, questions. There is one more thing remaining, which is the phasor diagram. So I will, we have time to get through that, but questions. Distribution. Yeah. Yeah, DC circuits would not have any impedance. Yeah. All right. Any other questions? Again, just as a recap, the first step, the absolute first step you should do is draw out the equivalent impedance diagram. Because once you have that, all you're doing there is you're replacing every single component with a resistor. So once you look at that, then it's like, think back to chapter 2. Okay. Once you have this equivalent impedance diagram, you think back to chapter 2, then the circuit doesn't look, as fearful. Analysis remains the same. Everything else remains the same. The only thing difference is the math. Okay. So you can do node voltage analysis, mesh current analysis. Is anyone interested in doing so? I guess not. But again, that's just math. And just in the interest of time, we just don't have enough time during a 10-week quarter to actually, get into all of those. But as engineers, if you're capable of performing complex math, then there is no reason why you would not be able to apply it to chapters 1 and 2. Okay. So phasor diagram. Let's draw out the phasors for all of the components. So let's do this. All right. And then let's see, I'm somewhere in the middle, would be here. Okay. Phasors and impedances we are representing as vectors, which are rotating counterclockwise in the complex plane. Real axis, imaginary axis. So if you have a phasor or a vector with magnitude and the phase angle, the only two things, those are the things you need to plot. So you first look at the phase angle. If it's a phase angle, let's say at 15 degrees plus positive 15 degrees, then it's rotating counterclockwise. Negative phase angle with reference to the zero axis, the real axis, rotates clockwise. So if you're plotting out, the first thing, let's say, is our voltage. Let's see, supply voltage Vs. Okay, supply voltage Vs has an angle of 30 degrees, plus 30 degrees. So as I said, a positive phase angle is rotating counterclockwise. A negative phase angle is rotating clockwise. Okay, so plus 30 degrees is going to be somewhere here. And I'm going to use a rainbow colored pen. And that's an approximation, of course. This is not to scale. So this is your phasor for Vs. Phasor for Vs. Okay. And this is going to be 30 degrees with the real axis. The length of the vector Vs is, of course, the voltage, which is, I can remember what it was right now. Vs is what? 100. So it's 100 volts. And obviously, this is not to scale. Okay, not to scale. Okay. Then the resistor voltage VR is at minus 15. So that should be somewhere here. And my resistor voltage in so this is VR and this is minus 15. I would not put a minus here because this is simply an angle. The minus would be obvious because my real axis is 0 degrees. Okay, so this is simply an angle of 15 degrees. Then current I for a resistor, if you remember, there is no phase difference between the voltage and current. So current I also has a phase of minus 15 with a magnitude of just 2. Yes. Absolutely correct. Clockwise, yeah. But the reference direction for a phasor or a vector is always counterclockwise. And so it always goes counterclockwise direction. Yeah. Let me plot out the other two, which is the, let's see, in blue, I'm going to plot out VL, the inductor voltage VL. So inductor voltage VL, which has a phase angle of 75. And then the capacitor, actually, you know what? Let's do this. VL and VC. Capacitor voltage is minus 105 and inductor is plus 75. This is only to the x-axis. And then if you see, inductor and capacitor are 180 degrees out of phase, which is what we would expect. And so that's the phasor diagram for all four quantities. Okay. All right, so quiz on Monday. As usual, the homework for this, I can't remember how many problems I had on here. I'm going to take a look at the average time. Typically, I would make it due Sunday night. But if it's going to take longer, maybe I might just extend it by a few hours. So again, I wish you a good weekend. Reach out to me over the weekend, Zoom, email. If you have any questions, I'll be happy to answer them. But again, I'll wish you a good weekend. I'll see you all on Monday. Yes. I haven't decided yet. So I'll post the announcement as usual by today evening or at least by tonight. Yeah. Okay.